You see something moving wrong across your telescope feed. Direction off, speed all wrong. July 1st, 2025, Rio Hurtado, Chile. The Atlas Survey Telescope catches something entering at 4.5 astronomical units out, punching through at 61 kilometers per second. They tag it A11PL3Z. 3 hours of watching and the numbers lock. This thing isn't orbiting, it's passing through. Third interstellar object ever confirmed. They name it 3I Atlas. Third visitor from somewhere beyond the sun's grip. The observatory code W68 marks the location. Rio Hurtado Station. Elevation 2,300 meters. Desert sky. Atlas network designed for asteroid detection. 4 telescopes total. Hawaii, 2 stations. South Africa 1. Chile 1. All watching for near-Earth threats. July 1st, 05:15:11, Universal Time. Discovery observation logged. Apparent magnitude 18. Faint but trackable. Moving through Serpens Cauda and Sagittarius border, near the galactic plane where stars crowd thick. If you value documented astronomical discoveries and hard spectroscopy like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from the ARCS of preprint server paper 2508.18209, published August 25th, 2025, by Martin Cordner at NASA Goddard Space Flight Center, and the Nature Astronomy paper analyzing the James Webb Space Telescope NIR spec observations, taken at 3.32 astronomical units from the Sun. Now back to the information. Palomar Observatory, San Diego County, California. Then Atlas had it June 25th going back. Amateur astronomer Sam Dean finds frames from June 5th. Nobody spotted it earlier because it crossed right in front of the galactic center. Dense star field, easy to miss. NASA's TESS satellite had watched it from May 7th to June 3rd when the comet sat 6.4 astronomical units out. Already bright, already active. Water doesn't sublimate at that distance, something else driving the show. Minor Planet Center receives the observations July 1st at 07:48 Universal Time. 2 hours, 33 minutes after discovery, initially listed on the Near-Earth Object Confirmation page. Orbit uncertain, could be dangerous. Trajectory calculations run. Within 13 days, 151 observations collected. Eccentricity range 2.9 to 4.5. Hyperbolic confirmed. No Earth threat. Closest approach to Earth, 1.8 astronomical units minimum, 270 million kilometers. Safe passage guaranteed. The velocity tells the story. 140,000 miles per hour. 221,000 kilometers per hour. Solar escape velocity at 4.5 AU is 14 kilometers per second. 3I Atlas moving 61 kilometers per second. Hyperbolic excess velocity 58 kilometers per second. That number means freedom, enough speed to leave the solar system forever, not captured, not bound, passing through. Teardrop cocoon of dust streaming off the nucleus. Stars streak in the exposure because Hubble tracks the comet. Moving target. Exposure time unknown, but long enough for star trails. Coma spans 26,400 by 24,700 kilometers, twice Earth's diameter. Nucleus estimate drops fast. Upper limit 5.6 kilometers by August 20th. Could be as small as 440 meters. Tiny visitor from outside. Largest single aperture optical telescope in the world. La Palma, Canary Islands. Images show elliptical coma, not perfectly round. Slight elongation, pressure effects maybe, or rotation, or jets from active areas creating asymmetry. NIR spec instrument. Near-infrared spectrograph. Integral field unit mode. Infrared range 0.6 to 5.3 micrometers. Heliocentric distance 3.32 astronomical units inbound. The spectrum comes back strange. Carbon dioxide dominates everything, not water. Carbon dioxide. 4.3 micrometer region shows massive carbon dioxide emission. Q branch emission, strongest feature in the entire spectrum. Water emission at 2.7 micrometers present but weak. Carbon monoxide at 4.7 micrometers detectable. Carbonyl sulfide tentative at 4.85 micrometers. 4.5 standard deviations above the trend line for every long period comet and Jupiter family comet ever measured between 3 and 4 astronomical units. Statistical analysis includes 47 previous comets, long period comets, Jupiter family comets, Halley type comets, all plotted against heliocentric distance, log linear, fit to the combined dataset. 3I Atlas sits way above the line. Over 80% carbon monoxide by molecular number, 12 to 17% carbon dioxide, 4 to 6% molecular nitrogen, trace water below 1%. Discovered September 7th, 2016. Pan-STARRS survey at Haleakala Observatory, Hawaii. Perihelion, May 18, 2018 at 2.6 astronomical units. Inbound orbit, 22,000 year period. Aphelion, 1600 astronomical units. Oort cloud comet, blue coma from ionized carbon monoxide. CO plus emission dominates visible spectrum. Molecular nitrogen detected, N2 plus ions. First comet with confirmed strong nitrogen. Chemical composition absolutely bizarre. Isotope ratios measured, carbon-12 to carbon-13 around 90. Solar system normal, argues against interstellar capture. But composition argues for it. Nobody resolved the contradiction yet. Two other historical comets show similar chemistry, C1908 R1 Morehouse, C1961 R1 Humason. Both blue, both CO-rich, both low dust, rare comet class, maybe 3 members total until now. CO2 dominance instead of CO dominance. Formation pathway distinct, ice line chemistry different, parent system different. But both comets shouting the same message. Planetary formation varies wildly across the galaxy. Spectrophotometer for the history of the universe, epoch of Ryanization and ICES Explorer, launched 2025. Mission designed to survey the entire sky. 102 different wavelength maps, deep red to mid-infrared, 0.75 to 5.0 microns. Earth's atmosphere blocks most of these wavelengths from ground telescopes. Water vapor absorption, carbon dioxide absorption, atmosphere opaque in key regions, space observation required. Not full spectroscopy like JWST, but wavelength specific. Symmetric cloud around the nucleus. Brightness falls off with distance to the negative 1.5 power in 2-dimensional projection. Actual 3-dimensional density drops radius to the negative 2.5, steeper than typical. Suggests high outgassing rate or unusual expansion velocity. Cloud extends 348,000 kilometers out. Measured radius in the image. Beyond that, emission drops below detection threshold. Reflected sunlight from nucleus and inner coma. Brightness suggests large object if solid. 46 kilometer diameter if the 1 micrometer emission comes from solid surface only. Makes no sense. Population statistics broken. We should see thousands of smaller objects before one that large. Rarity argument fails. More likely explanation. Coma contamination. Gas and dust scatter sunlight. Add to nucleus reflection. Apparent brightness inflated. True nucleus smaller, under 1 kilometer probably. The instrument also images at 3.0 micrometers targeting water and 4.7 micrometers targeting carbon monoxide. No strong coma detected in water band, no gas emission, only surface ice reflection. Carbon monoxide image shows weak signal. Present but not dominant like carbon dioxide. Confirms AWST results. CO2 is King in 3i Atlas. Organics mixed in. Spectral shape similar to Kuiper belt objects, trans-Neptunian objects, cold classical objects. Surfaces processed by cosmic rays for billions of years. Radiation chemistry converts simple ices to complex organics. Tholins form. Reddish color develops. 3i Atlas shows this signature. Ancient surface, long exposure to interstellar radiation. Elevation 2,700 meters. Near-infrared spectroscopy, 3 to 5 micrometer range. Water emission bands detected. Production rate calculated. Still low compared to carbon dioxide. NASA Infrared Telescope Facility, 3-meter telescope, Mauna Kea, Hawaii. Elevation 4,200 meters. Infrared optimized. Multiple observation nights. Water production rate rising, but carbon dioxide still dominant. Ultraviolet and X-ray instruments. Designed for gamma-ray burst follow-up. Pointed at 3i Atlas during gap in primary mission. Ultraviolet spectroscopy. Hydroxyl emission at 309 nanometers. Water photodissociation product. H2O breaks. OH radical forms. Fluoresces in UV. Detection confirms water outgassing, but ratio calculation still shows carbon dioxide domination. 8 parts. CO, 2 to 1 part, water persists. Not elevated like Borisov. 2i Borisov showed 35 to 155% CO to water. Absurdly high. Higher than any solar system comet observed in inner regions within 3 AU. Came from around a red dwarf star, hypothesis suggests. Low luminosity star, low temperature. CO ice line far from star. Cold enough for carbon monoxide ice to dominate planetesimal composition in the outer disk. Formation region maybe 10 to 20 AU from a 0.5 solar mass star. Equivalent to 30 to 40 AU in our system, way out past Neptune. Water ice line sits around 2.7 astronomical units in our system. Temperature 150 to 170 Kelvin. Carbon dioxide ice line, 9.3 astronomical units. It uses the minimum mass solar nebula model, Hayashi calculation from 1985. Temperature drops below CO2 condensation point. Beyond that line, carbon dioxide freezes solid onto dust grains, water already locked up closer in. If 3I Atlas formed just beyond the carbon dioxide ice line in its home system, the chemistry fits. Water at 2.7 micrometers, carbon monoxide at 4.7 micrometers, carbonyl sulfide detected tentative, OCS gas, rare find. Dust scattering at 1.2 micrometers shows the Coma shape, enhanced outgassing sunward, pressure from solar radiation. Normal comet behavior in an abnormal comet. Not evidence of a radically alien chemistry, just different proportions. Carbon monoxide more likely. Supervolatiles driving early activity. By August, at 3.32 astronomical units, carbon dioxide takes over. Production rate calculation from the 4.3 micrometer band strength. Sunward enhancement visible in spatial maps. Nucleus heating unevenly. Rotation bringing fresh ice to the sun-facing side. Cass's camera on trace gas orbiter designed to photograph Mars' surface from hundreds to thousands of kilometers. Instead, aims at a faint dot 30 million kilometers distant. Faint white spot in the frames. Glowing Coma visible. Comet more active by then. Closer to the sun. October 30th, perihelion, 1.4 astronomical units, just inside Mars orbit. Transmission rate too low. JUICE sees the comet post-perihelion, more active state. Water production likely turned on full by then. Or formation near the CO2 ice line where carbon dioxide ice dominates over water, or thermal properties of the nucleus. If heat doesn't penetrate deep, surface ices sublimate first. Carbon dioxide has lower vapor pressure than water at the same temperature, melts first. Carries away before water wakes up. If 3I Atlas formed that far out, nitrogen should show. Current measurements don't detect strong N2 emission, suggests formation inside the nitrogen line, likely between the CO2 line and maybe 15 to 20 astronomical units. Still far, still cold, but not trans-Neptunian cold. Density constraints come from the dust, low dust-to-gas ratio, Coma brightness, mostly from gas emission, and scattered sunlight off small particles. No massive dust tail. Hubble image. July 21st shows teardrop shape, but no strong tail structure, compact Coma. By mid-August, SphereX images show point source, no resolved dust cloud. Gas dominates carbon dioxide gas. Object that large, we'd see thousands before one this big. Rarity argument breaks. More likely, bright Coma contamination, actual nucleus smaller. Hubble constraints from August 20th say upper limit 5.6 kilometers, lower limit 440 meters. Probably less than 1 kilometer. Similar to 2I Borisov. Mass estimate drops accordingly. Dust loss rate backs the small nucleus model. Carbon dioxide sublimates freely. Water ice threshold 170 to 180 Kelvin. Close, but not quite. Depends on sun angle, thermal inertia, dust coverage. If dark dust layer covers water ice patches, insulation effect. Carbon dioxide outgasses from cracks and vents. Water stays locked until closer in, or until surface erosion exposes fresh ice. Retrograde orbit, 175-degree inclination to Earth's orbital plane, not from the thin disk of the galaxy. Thick disk, maybe. Galactic halo possible. Age estimate? 2 to 3 times older than solar system comets if thick disk origin. 7 to 10 billion years old. Ancient ice. Closest approach to Earth? 1.8 astronomical units. No threat. 270 million kilometers minimum, visible through September from ground telescopes. October obscured by the sun, reappears early December outbound. By then, most volatiles already lost. Coma fading. Dust tail may be visible, water finally sublimating freely after perihelion heat. But the observation window narrows fast, moving away at breakneck speed. Gone by early 2026 from easy observation. 2I Borisov discovered August 30th, 2019. First confirmed interstellar comet. Showed clear Coma from discovery. Active. CO to water ratio 35 to 155%. Absurdly high. Only one solar system comet higher. See 2016 R2. 3I Atlas flips the script. CO normal. CO2 extreme, different formation pathway, different parent system maybe. 3I Atlas shows early carbon dioxide before water even starts. Surface composition different, or nucleus structure different, or both. Dust characteristics different, small particle size distribution, less processed, more pristine. If 3I Atlas shows similar polarimetry when measured, supports pristine formation hypothesis. If not, different dust evolution history in its birth system. Red dwarf likely for Borisov. low luminosity, low temperature, CO line far from star, cold enough for carbon monoxide ice to dominate planetesimal composition, 3I Atlas parent, if CO2 rich, maybe slightly warmer star, K-type or late G-type, or farther orbit around similar star. CO, 2 line at 9.3 AU in solar system. Could be 12 to 15 AU in a cooler system, 15 to 20 in a warmer one. Formation location matters for composition. Less heavy elements means different chemistry in the protoplanetary disk. Carbon and oxygen still abundant, but ratios between different carbon-oxygen compounds shift, maybe favors carbon dioxide formation over carbon monoxide. Stellar radiation environment matters too. UV flux from parent star drives photochemistry in the disk. Different UV means different ice chemistry. Break chemical bonds, forge new compounds. Over billions of years, outer layers of drifting comets get cooked by radiation. Water converts to hydrogen peroxide, carbon monoxide to carbon dioxide. Organics form from simple molecules. If 3I Atlas spent 4 billion years minimum in interstellar space, radiation should process the surface heavily. Thick, irradiated crust forms. First layers to sublimate near the sun, irradiated ice, carbon dioxide rich from radiation chemistry. But spectroscopy argues against heavy processing. Carbon isotope ratio, normal. Heavy processing by cosmic rays tends to fractionate isotopes. Enrich heavier isotopes. 13C should climb relative to 12C. 3I Atlas shows Earth-like ratio. Suggests either minimal processing time or continuous refreshment of surface ice. Maybe nucleus active enough to resurface regularly. Or maybe interstellar journey shorter than expected. Not 4 billion years? Maybe 1 billion. Still ancient, but less cosmic ray dose. The nitrogen clue matters here. C2016R2 shows strong molecular nitrogen, 4 to 6% by molecules. 3I Atlas, no strong N2 detection yet. Nitrogen has isotopes too, 14N and 15N. Ratios in comets vary. Measurements from molecular nitrogen ions directly in C2016R2 gave isotope ratios. 3I Atlas nitrogen measurements pending. If measured and if isotopes look solar system normal, argues for similar formation environment despite interstellar origin. If weird, argues for genuinely alien chemistry. Sulfur compounds hint at formation conditions. High sulfur in protoplanetary disk material, or specific temperature and pressure during ice condensation. OCS forms from reactions between simpler sulfur and carbon compounds. Presence suggests active chemistry in the birth disk, not just passive condensation. Thermal fractures, pockets of pressurized gas breaching surface, fragmentation possible like Borisov showed. Borisov broke apart slightly, pieces separating. 3I Atlas structural integrity unknown. Size matters. Smaller means weaker, more likely to fragment, but also heats faster. Could lose volatiles before stress accumulates enough to crack it. Dust tail most prominent feature by then. Solar radiation pressure pushes dust anti-sunward. Tail stretches, ground telescopes can track it. Measure dust particle sizes from brightness and color. Particle size distribution tells stories about formation. Large grains mean weak aggregation. Small grains mean strong processing. Brightness varies with rotation period. Isotropic emission means uniform activity or many small vents distributed evenly. 3I Atlas showed sunward enhancement in August. Suggests partial activity, some area more active than others. 2I Borisov fragmented slightly. Lost pieces, dust production spiked. 3I Atlas, unknown until perihelion passage completes. If it fragments, pieces separate slowly. Mutual gravity weak, relative velocity meters per second. Takes days to separate noticeably. Follow-up imaging required to catch it. If fragments, multiplies data points. Each piece different composition maybe, sample different layers of the nucleus, or maybe homogeneous. All pieces identical chemistry. That would tell us about mixing in the birth disk. Homogeneous suggests small formation region. Heterogeneous suggests wide range of distances swept up. Field of regard limited. If 3I Atlas crosses into safe zone, JWST could grab another spectrum. Compare to August measurements. See how chemistry evolved. Water fraction, probably higher. Carbon dioxide spent, deeper ice exposed. Maybe different carbon isotope ratio if layered heterogeneity exists. 3. I Atlas CO, already measured around 1.4 ratio to water in August. Should climb as water production increases. Ratio might stabilize around 2 to 5% typical range, or stay high if nucleus intrinsically Keough-rich too. ALMA can map the gas distribution, spatial structure. Jets versus uniform outgassing. Expansion velocity from line profiles. Typical expansion velocity, half kilometer per second. 3i Atlas measured 0.50 plus or minus 0.15 kilometers per second in early observations. Normal range. The amateur astronomer community contributes. Light curves from backyard telescopes, magnitude measurements nightly, track brightness changes, outburst detection. Professionals can't monitor continuously. Too many demands on telescope time. Amateurs fill gaps. Citizen science critical. Someone caught the June 5th pre-discovery observation already. More observers means better coverage, means more science. Silicates have features at specific wavelengths, organics have others. 3i Atlas showed reddish color in early visible light observations, common for comets. Organics coating dust grains, tholins, complex organic molecules formed from radiation processing of simpler ices. Methane, ammonia, water, irradiated for eons, produces reddish brown gunk. Tholins, detected in solar system comets. Expected in interstellar comets too, if formation environments similar. Atomic emission from sublimating metal-bearing grains. Temperatures high enough near the sun, metals vaporize, fluoresce under solar UV. 3i Atlas, metal detections pending. Swift observatory UV spectroscopy might catch it, or ground-based high-resolution optical spectroscopy. Metals tell stories about rocky component mixed with ice. Chondritic composition expected, similar to carbonaceous chondrite meteorites, but ratios might differ. Parent star metallicity affects dust composition. Lower metallicity star means less iron and nickel. Higher means more. The dynamical story matters. 3i Atlas entered from Sagittarius. Hyperbolic velocity 58 kilometers per second. Implies ejection from parent system at similar speed. How do comets get ejected at 58 kilometers per second? Giant planet encounters. Close approach to Jupiter-mass planet, or larger. Gravitational slingshot. Typical ejection velocities from planetary scattering 10 to 30 kilometers per second for solar system. Higher for more massive planets, or tighter encounters, or binary star systems. Two stars orbiting each other. Comet passes between, gets accelerated by both. Ejection speeds can hit 50 to 70 kilometers per second. Maybe several. Scattered disk analog in the parent system. Comets form an outer disk. Planets migrate inward or outward. Scattering events. Some comets inward to become short period, others outward to Oort cloud analog. Still others ejected completely. Interstellar space. 3i Atlas got ejected. Billions of years ago, a thick disk wandered the galaxy. Happened to cross paths with solar system. Probability microscopic. But galaxy has hundreds of billions of stars, hundreds of billions of planetary systems probably, trillions of comets total, some fraction ejected. Means interstellar comets everywhere. We see them rarely because space, huge. Detection requires lucky alignment and good timing. 3. I Atlas came from different part of the galaxy maybe, different orbit. Relative velocity builds up, 58 kilometers per second, hyperbolic excess from solar system perspective, but parent star might be moving 30 kilometers per second relative to the sun. Add vectors. Ejection velocity from parent system maybe 30 to 40. More reasonable. Dynamical studies needed, backtrack trajectory, find possible parent stars, stars moving through that region of space, similar velocities. Age is consistent with ejection time. Needles in haystack, but calculations possible. Gaia satellite data helps. Astrometry for billions of stars, positions and velocities. Backtrack 3, I-Atlas orbit. Backtrack star motions. Find intersections in space and time, millions of years ago maybe, or tens of millions. Parent star identification difficult. Uncertainties accumulate. But rough neighborhood determinable. Thick disk versus thin disk, question answerable. Galactic coordinates of origin point toward thick disk. Older stellar population, lower metallicity, fits the age estimate, confirms ancient origin hypothesis. Could 3i Atlas have formed in the solar system? Ejected early, captured back by chance, probability infinitesimal. Solar system ejection velocities not high enough to create 58 km per second hyperbolic excess. Would require 70 kilometers per second minimum at ejection. Early solar system chaotic, giant planets migrating, nice model, jumping Jupiter. But ejection speeds rarely exceed 35 kilometers per second. 3i Atlas, too fast. Must be genuinely interstellar. Same argument for Borisov, too fast for solar system origin. First interstellar object, October 2017. Small, elongated, no coma detected. Accelerated non-gravitationally, outgassing or something else. Composition unknown, too faint for spectroscopy, left too fast. 3i Atlas, second active interstellar visitor. Better data, clear comet, Coma. Gas emission, dust, icy nucleus, spectroscopy locked, composition measured, chemistry analyzed, story emerging. 3I Atlas, CO2 rich. Solar system comets mostly water rich, with CO and CO2 subordinate. 3 populations maybe, or continuum, more detections needed. Vera Rubin Observatory comes online fully. Legacy Survey of Space and Time, LSST, surveys the whole sky repeatedly. Finds faint moving objects. Expected to catch dozens of interstellar objects per year once running. Sample size will explode. 3I Atlas becomes one of many. Statistics improve. Formation model testing possible. Water molecules. Deuterium heavy hydrogen, extra neutron, forms in cold environments. Protosolar nebula had D to H around 2 times 10 to the negative 5th. Earth's oceans higher, 1.56 times 10 to the negative 4th. Some comets match Earth, others higher, some lower. 3I Atlas D to H not measured yet. A water 2 week in August, post-perihelion measurements possible. If D to H matches solar system, suggests similar formation conditions. If way off, alien formation proven. Oxygen isotopes matter too, 17O and 18O relative to 16O. Solar system comets cluster in narrow range. Interstellar comet outside range proves different birth environment. 3I Atlas HCN not detected strongly. Carbon dioxide dominates so heavily, other species suppressed or hidden in noise. Methanol might be there. Formaldehyde possible. High resolution spectroscopy needed. JWST capable, but expensive. Telescope time allocated tightly. Follow-up campaigns require strong justification. Early results justify more observation. CO2 dominance anomaly enough. Approved observation time likely. December follow-up probable. Data by early 2026. Crystal structure of silicates. Amorphous versus crystalline. Temperature history. Protoplanetary disk temperature determines crystal structure. Hot inner disk, crystalline silicates form. Olivine, pyroxene. Cold outer disk, amorphous silicates dominate. If 3I Atlas dust shows crystalline silicates, suggests radial mixing in birth disk, hot dust transported outward, mixed with cold ice, formed nucleus with both, infrared spectroscopy detects silicate features, 10 micrometer region, JWST MARI instrument capable, observations, pending maybe. Density constraints tighten, nucleus mass from non-gravitational forces, outgassing produces thrust, accelerates comet slightly, detectable in orbital solution, precise astrometry required, long baseline. 3I Atlas discovered July 1st, perihelion October 30th. Outbound through November, December, January. Astrometry through February or March 2026 before too faint. 6 to 9 month baseline. Enough for non-gravitational parameter measurement, mass and density derived. Typical comet densities 500 to 600 kilograms per cubic meter. Fluffy, porous. 3I Atlas probably similar unless unusually icy. More ice than rock means lower density, 400 kilograms per cubic meter possible, or unusual rock fraction, higher density. Rotation period unknown, light curve amplitude needed, brightness variations over hours. If rotating, brightness cycles, maximum brightness when long axis perpendicular to line of sight, minimum when parallel. Amplitude depends on axis ratio. Elongated nucleus, high amplitude. Spherical, low amplitude. 3I Atlas light curve data sparse. Perihelion passage might bring outbursts that mask rotation signal, or jets introduce non-rotation variations. Fourier analysis needed, separate rotation from other effects. Period might be hours. 6 to 12 hours, typical for small comets, or days of slow rotator. Spin rate affects surface temperature distribution. Fast spin, uniform temperature. Slow spin, hot day side, cold night side. Affects activity pattern. Estimates range from 0.1 to few per year detectable. Depends on survey depth. Vera Rubin detects to magnitude 24.5. Faint enough to catch most within Jupiter orbit. Maybe 5 to 10 per year. Some active, some inactive. Active easier to detect. Coma brightness helps. Inactive harder. Asteroidal signature. Have to rely on hyperbolic orbit detection. Harder, but doable. Population models suggest 10,000 to 100,000 interstellar objects closer than Neptune at any time. Vast majority too small or too faint. We see only the lucky few, bright enough. Close enough, right time. Formation model testing becomes rigorous. Right now, 2 active interstellar comets. Suggestive, but not conclusive. 10 comets, strong constraints. 50, model selection possible. Which protoplanetary disk chemistry models match observed distributions? Temperature profiles and birth disks? ice line locations, radial mixing efficiency, all testable with large samples. 3. I-Atlas and Borisov differ significantly. Suggests diversity, more samples needed to confirm. Could be selection bias. We detect comets active near the sun. Misses comets that sublimate too early or stay inactive. Compositional bias in detected population. Corrections needed. Statistical modeling. Account for detection efficiency as function of composition. Complicated but necessary for population inference. Orbits from days to thousands of years. Where do comets form in those systems? Do hot Jupiter systems eject more comets because of strong scattering, or fewer because disk depleted early? Do systems with multiple giant planets produce more interstellar comets? Dynamical simulations suggest yes. Multi-planet systems unstable early on, scattering events common, comets ejected in bulk. 3 I-Atlas might come from such a system. Multiple giants, chaotic early phase. Nucleus formed at 10 to 15 AU, got scattered by planet at 5 AU, encountered another planet at 20 AU. Final kick sent it interstellar. If 3 I-Atlas parent star 7 billion years old, and comet ejected early in system history, spent 6 billion years wandering. If ejected late, maybe only 1 billion years interstellar. Age affects surface processing. Radiation dose accumulates with time. Ice chemistry evolves. Cosmic ray hits convert CO to CO2 over gigayear timescales. If 3 I-Atlas showed 6 billion years processing, surface layer entirely CO2 from radiation. Buried CO and water underneath. First to sublimate, irradiated CO2. Explains dominance, or maybe formed CO2, rich intrinsically. Both scenarios fit current data. Isotope measurements might distinguish. 3 I-Atlas caught at magnitude 18 at discovery. Barely. If dimmer, missed entirely. How many interstellar comets pass undetected? Models suggest several per year within Jupiter orbit. We catch maybe 10%. LSST will catch higher fraction. Deeper, wider, faster surveys detect more. But never 100%. Always objects too small or wrong location. Trade-off between data quality and object brightness. Eventually too faint for useful data. Cutoff maybe May 2026 for large telescopes. July for Hubble, September for JWST if geometry allows. After that, gone until way in the future if orbit perturbed. Or gone forever if left solar system cleanly, no more encounters. Comparisons to solar system comets and Borisov quantified. 3 I-Atlas takes its place in the catalog. Third interstellar object. Second confirmed comet. Most carbon dioxide-rich interstellar visitor. Formed beyond the CO2 ice line in a distant planetary system billions of years ago. Ejected by giant planets, wandered the galaxy for billions of years. Entered the solar system July 2025. Observed by every major telescope. Spectroscopy from JWST. Chemistry measured. Story told. The 13CO2 detection. Carbon isotope ratio calculated from the weak band at 4.4 micrometers. Ratio comes back 12C to 13C around 90. Solar system value 89, Earth value 89. 3 I-Atlas matches exactly. Despite billions of years in interstellar space, despite formation around a different star, despite entirely alien planetary system origin. The carbon that built 3 I-Atlas came from the same galactic reservoir that built Earth. Same supernova enrichment, same molecular cloud chemistry. Same protosolar nebula processes, just different star. We are not sampling a foreign chemistry. We are sampling our own galaxy's baseline. Interstellar comets are not aliens. They are neighbors. Different birth, same ingredients, same story, just told around a different star. Frozen carbon dioxide sublimates under the Chilean sunrise, and somewhere in the thick disk, another star watches its own comets scatter into the dark.